I don't know why I'm so confused. Probably. What are we like after we do like so for the first one, the 8.1-12?
Mm-hmm.
After we do the like normal.
Oh, splitting it up into pieces, yeah.
Yeah, after you do that, and you like do the count ifs.
Mm-hmm.
How are you supposed to like know?
So those are the count ifs will be your observed.
Yeah.
Right.
Oh, and then you do the
expected, since you're breaking it up into equal intervals of equal probability, they're all the same.
Mm-hmm.
So I don't remember what the sample size was.
I think it's like 90.
90. So, yeah, it'd be split. Yeah. So if you split it into 10 pieces, it'd be 9 in each one.
When's the homework due?
Wednesday. Right? Is it Wednesday? Yeah. That sounds familiar.
That's what I thought. Just double check.
Other questions? No? All right, so last time we talked about bias. So let's look at number that 24.3 that I just handed out. So they have a random variable, binomial random variable, I should say, where you got M and Q is the parameters, and Q hat is the estimator for X over M. And in terms of Q hat, it's looking for an unbiased estimator of the Q times 1 minus Q. So what would be your first guess at what might be an estimator for Q times 1 minus Q? We're not worrying about bias or anything along those lines. If you're using Q hat to estimate Q, what do you think you would use to estimate Q times 1 minus Q? Yeah, that would be your first guess, right? So the first thing you would do is look and just try to use Q hat times 1 minus Q hat as your estimator and see what happens. If it's going to be unbiased, when we take the expected value, what should we get? Well, the bias should be 0. The expected value should be the parameter you're trying to estimate, right? So let's just look at the expected value of Q hat times 1 minus Q hat. Yeah. So the way we're calculating I'm just going to multiply it through. So you have Q hat minus Q hat squared. So I can split up the expected value over the difference. And I already know what this is, what I'm underlining here. What is expected value of Q hat? They tell you. Well, X over M is what Q hat's defined as. What's the expected value? It's the next sentence.
Q.
Yeah, it's Q, right? It says it is an unbiased estimator of Q, right? So it has to be Q. All right. So I need to figure out the expected value of Q hat squared, though, still. Right? Probably, at least for me, the easiest way to do that is to rewrite the expected value of Q hat squared in terms of its variance and its expected value. We know variance is expected value of x, just in general with x's. Variance of x is expected value of x squared minus expected value of x quantity squared. So expected value of x squared would be variance of x plus expected value of x quantity squared. So I can replace this with variance of Q hat plus expected value of Q hat squared. Right? We agree? Just using the formula for variance that we typically use to calculate variance and just rearranging it. Adding expected value squared to the other side. Now do we know these pieces? Well, I do know, I'll do variance of Q by itself. We know that expected value of Q hat, the screen went.
Oh, it's fine. I'm going to touch it.
Don't breathe on it. Expected value, that's weird. Expected value of Q hat is Q, right? So we have a minus Q squared there. So we need to figure out this piece. So this is where we'll actually use the definition of our, at least for me, I think it's easier just to use the definition of Q hat. Or you could also think about doing central limit theorem as well. I think it's just easier to rewrite this as your x over m, right? Because that's how Q hat's defined. So I want to simplify that. What can I do with the m?
Take it out.
And make it squared. Good. And then what kind of random variable is x again? Binomial. So what's its variance? It's one of those we know. What's the variance of binomial? And there's an extra piece. Yeah, there's an n, right? So in this case, your n is m and your p is q, right? So this will be m times q times 1 minus q. So certainly the m on top will cancel with 1 on the bottom. Notice that our first term and our last term is also a q times 1 minus q, isn't it? So you have q times 1 minus q minus 1 over m times 1 minus q. Or this would be m minus 1 over m times 1 minus q. All right, so that's what we got when we took the expected value. That's how we started this, right?
Where did the Q go in the middle?
Oh, yeah, I forgot to write it. Okay. Sorry, it's supposed to be there. Okay. I just forgot to write it. So this is what the expected value is. What if it's going to be unbiased? What needs to go away?
The front part.
Yeah, the front part, this part needs to go away, right? So what do we need to put in front here so that this part goes away? What? Yeah, the m over n minus 1, right? Do 1 over it, exactly. Yeah, do 1 over that one. So we should have E for the answer then? Does that make sense? You okay with that? All right, let's look at 4. So this one's just asking us about properties of these things. If you look at 24.4, it says we've got a random sample from a Poisson distribution, and it asks you to calculate the 3 statistics as estimators for lambda. 1's the sample mean. What's 2?
Which one were we looking at?
24.4, the one right below it. So 1 is the sample mean. What's 2? What statistic is 2? It's the sample variance, right? And then 3 is just a linear combination of the x1 and the x2. So ignore the fact that we've got a Poisson. For 1 and 2, 1 is the sample mean. What is the expected value of the sample mean, just in general? What's it always equal to? The population mean, right? No matter what, and it's always unbiased, right? Right? So 1 is, I'm ignoring the fact that it even says Poisson. I'm just talking about it in general, right? The expected value of your sample mean is the population mean. So the sample mean is always an unbiased estimator for the population mean, no matter what. Okay. 2 is the sample variance, and the reason why we divide by n minus 1 instead of dividing by n is because of the bias, right? Remember we talked about that before? That the expected value, if you just divide by n, isn't quite right? We had to divide by the n minus 1 to get it to work right? So no matter what the distribution is, the sample variance is always an unbiased estimator for the population variance. And then 3 is just a linear combination. But notice that if x1 and x2 are the same, randomly chosen from the same distribution, the expected value of the first one is going to be 2 times the expected value of the second one. So you're just going to get the population mean out of that one. So 3 there will be an unbiased estimate, or an unbiased, estimator for the population mean as well. So I wanted to make sure that I emphasized 1 and 2. 1 and 2 being unbiased estimators for the population parameter has nothing to do with the fact that it's Poisson. Those are true in general. Okay. Now let's go to Poisson, because it's asking you to estimate lambda, right? Well, lambda is the mean of the distribution, so 1 is definitely unbiased for lambda, right? For Poisson, what's the variance for Poisson?
Lambda.
It's also lambda, right? So 2 is also unbiased for lambda. And then again, if you do for 3, if you do the expected value of that, just to write it down, if you do the expected value of 2x1 minus x2, I can break it up as 2 times expected value of x1 minus expected value of x2. But expected value of x1 and x2 are both what? Lambda. So we just get lambda. So that one's also unbiased. So the answer in that one will be D. that okay? All right. So let's talk about a couple of other properties of estimators. To that end, though, we need to get a little bit of background, especially for what we refer to as consistency. So, like I mentioned before on Friday, that I'm going to jump around in the book a little bit. Basically, I'm trying to take out the more straightforward things that are going on in Chapter 10 for this test, and then put the harder things towards the end, so that you'll have a take-home test on that part.
I forgot. Did you say the exam, the take-home one, is just over the last part? Over?
It'll be over everything, but
Okay.
yeah. So that's why I'm going to give it to you a little bit earlier, so you can start working on stuff the earlier stuff with, and then even if we haven't finished everything yet.
Okay.
That was my plan. All right. So I'm going to jump ahead to in the book to section 10.5, which talks about Chebyshev's inequality.
Is that one word or two?
What one? Oh, it's one word. Sorry. All right. So you may have seen Chebyshev's inequality before. It's a very, very interesting theorem in general. It's just the outcome that it gives you isn't the most robust outcome that you can get for specific types of distributions. But the cool thing about it is it works for no matter what distribution you have. So it says the theorem is, we're going to let x be any random variable. Oops. With mean mu and variance sigma squared. For any k that's bigger than or equal to 1, we have that the probability of x minus mu, the absolute value of x minus mu, being less than or equal to k times sigma is equal to, oops, sorry, not equal to, is greater than or equal to 1 minus 1 over k squared. Notice why we want k to be bigger than or equal to 1. If you put k equal to 1 in there, you're already, what do you get on the right-hand side? 0, right? So it says that just says the probability is bigger than or equal to 0, which is true, right? And if k is less than 0, then you've got issues because it's going to try to make that, if it's less than 1, then you've got issues with the bound in there. Anyway, in particular, what this is saying is giving you an idea of the spread of any distribution. So k times sigma is counting standard deviations. So what Chebyshev's inequality says is that the probability that a data point is within 1 standard deviation of the mean is greater than 0, which we already knew. But the probability that any data point for any distribution is within 2 standard deviations is at least 75%, because k would be 2 in that case, so you'd have 1 over minus a quarter. So no matter what the distribution is, literally, no matter what the distribution is, the probability that your data point is within 2 standard deviations of the mean is at least 0.75. That's a pretty big statement. And then likewise, if you do within 3 standard deviations, it's within 0.8 repeating, 8 nines, if you put in 3 for k. Okay, so that's a really interesting statement for the spread of any data set. Doesn't have to be exponential, doesn't have to be Poisson, doesn't have to be normal, binomial, whatever. It says any data set, it tells you how the data are spread out. Now again, it's not the best bound in the world because, of course, what did we just say a little bit ago? It says the probability that you are within one standard deviation of the mean is at least 0. Well, yeah, no kidding. Okay, so it's not the best bound in the world. We know for things for like the normal distribution, we know it's even better, right? Because for the normal distribution, it's about 68.34% lie within one standard deviation, 95% about lie within 2, 99.7 about lies within 3. So those bounds are not great for normal. But again, this is a statement for any distribution, not just the normal distribution or exponential for distribution or what have you. That's the cool part about this theorem. So let's prove it. Because if it's a cool theorem, we should prove it, right? At least in my estimation. Okay. So let's let F be the PMF or PDF of X. The way the book proves it is with PMF, so it's using sums. If you did PDF, you could do integrals. It's the same idea. That's how we define our variance, right? You sum up over all the x's in the sample space the square of the distance that x minus mu is from f of x, right? We agree? Okay. So what we're going to do is we're going to split this sample space into two pieces. So we're going to let A be the set of all x's such that the absolute value of x minus mu is less than k times sigma, less than or equal to. Well, then S, our sample space, is made up of A and its complement, right? And since, of course, they're disjoint, I can literally just split that into two pieces. Add up this thing over everything that's in A, and add up this thing over everything that's in A complement, right? We agree? So our sigma squared here will be the sum over everything in A plus the sum over everything in A complement. All right. So far, so good? Okay, so certainly F is a PMF or a PDF, and again, if you're doing PDF, you can just replace the summation with an integral sign, right? Right? So it doesn't matter. Certainly, it's a PMF or a PDF, so it's non-negative. And certainly, no matter what, if we square, it's non-negative. So if I drop one of these terms off, I don't know, I've got a minus sign looking thing in there. Oh, that's because I underlined the squared. That's why. If I drop one of the terms off, it would make the sum on the right-hand side smaller. Right? No matter which one I do. You agree? Now, the way I've defined, I would make it smaller so the variance would be at least as big. Okay? Now, the way I've defined A, I defined it as a less than inequality. So I probably don't want to drop off this part because I've got a greater than and then I got something with a less than inside the sum. So I'm going to drop off this part and write sigma squared is greater than or equal to the sum x in A prime, x minus mu squared f of x. Now, why did I do it that way? Anything in A, its absolute value is less than or equal to k times sigma, right? Do you agree? Anything that's in A, the absolute value of x minus mu is less than k times sigma. So if you're in A prime, what can you say about the absolute value of x minus mu? It's greater than, right? Do you agree? Okay. So what about if I square that then? What can I say about x minus mu squared? What's it going to be greater than? And then squared, right? Because if I square the absolute value would just go away, right? If you're looking at absolute value of x minus mu is greater than k times sigma, then x minus mu squared will be greater than k squared sigma squared, right? We agree? So on the inside there, I can replace that with a strict inequality. This will be the summation for all x in A prime of k squared sigma squared f of x.
So, where the x minus mu?
You just told me it was bigger than.
Bigger than that?
Yeah, it's bigger than that, yeah. The x minus mu squared is bigger than this, right? That's where it went. I just replaced it. I substituted and changed the inequality. Now, why did I want to do that? Well, what can I do with the k squared sigma squared? I can bring it out in front, right? We agree? And then I can divide it to the other side and get 1 over k squared is greater than this. But what is the right-hand side? Oops, sorry, that's an A prime. What is the right side? If you actually just computed it, what would the right side be equal to? You're thinking about it, right? But it's not quite 1.
Yeah.
Or we're only taking the x's in A prime.
1 minus.
Well, the 1 minus part is going to be coming in, but just in general, if we were just going to compute this thing, as a probability, what would it be? What are we doing? We're putting in the x in the PMF and adding it all up. What are we computing? Thinking too hard. What are we computing here in terms of probability? Well, part of it. It's not quite the CDF because we're not starting at the lowest point necessarily. Yeah, it's just a probability, isn't it? Probability that what? Yeah, the probability that we feel that we're in the complement, isn't it? This is just the probability that x is in A prime. That's all it is. Right? We're just adding up all the probabilities that x is in the complement. So now if we rearrange, you just told me this is 1 minus something, right? That'd be 1 minus the probability that x is in A. And then, well, how did I define A? That was this up here, wasn't it? So we'll get the probability that absolute value of x minus mu is less than or equal to k sigma is greater than 1 minus 1 over k squared. So, to give an example here, let's just look at 10.5 dash, well, let's look at 10.5 dash 2.
That's in the book.
Yeah, it's in the book, yeah. Sorry. So they tell you that the expected value of x is 17, and the expected value of x squared is 298. Part A says find a lower bound for the probability that 10 is less than x is less than 24. Bless you. All right, so we want to try to write this in terms of Chebyshev's inequality so that we can figure out what that lower bound is. So that's Chebyshev's inequality, all right? Notice by lower bound, it means that we're showing that the probability is greater than something. That's what the lower bound part means. So notice that the form of this is to write it as an absolute value statement is less than or equal to something. And by the way, if this equal to sign here goes away, if I erase it, maybe. If I just have this, then an equal to sign pops up here. It just flips between the two. Okay. Anyway. So notice I need to see an absolute value statement of x minus the mean. So the first thing I want to do in this probability that we're trying to do is make that inside piece of that inequality be an x minus the mean. Well, in this case, what is the mean? 17. So I'm going to subtract 17 from everything. So you get negative 7 is less than x minus 17 is less than 7. Can I convert that to an inequality statement? Or an absolute value statement? Sorry, an absolute value inequality. What would have to be true about the absolute value of x minus 17? It just has to be less than 7, right? Right? All right, so how does the 7 relate to number of standard deviations? So the reason why we did this first is because that's the form that Chebyshev's inequality takes, right? How far a data point is from the mean. So the right-hand side, though, here, I need to write it as a certain number of standard deviations away. So how am I going to figure out this part here? What do I need to do? Yeah, good. Got to find this variance, got to find the standard deviation, right? And then figure out what 7 is in terms of that. Good. So the variance is what in this case? 9, good. So that tells us that the standard deviation is 3. So rewriting this like this part here, those would be less than 7/3 times 3, right? And the reason why I wrote it that way is because what's your K? 7/3. This is the K, right? This is your K, this is your sigma. So this will be now greater than or equal to 1 minus 1 over 7/3 squared, which will be, what, 40 over 49?
Sorry, how do we get 3
Did you get 9? How do you calculate variance?
298 minus 17 squared.
Yep.
Yeah, I just did it wrong.
Yeah. Should be 298 minus 289.
Oh, yeah. Just did it wrong.
Okay. I'm used to doing that. Just teasing. All right. So there's our lower. Yeah, Kelly. This is the lower bound. The inequality gives you a lower bound when it's in this form because it says it's the probability has to be greater than that. So it automatically gives you a lower bound. Just because of the way the inequality points. So when you look at part B, where it asks you to find an upper bound, for the probability that absolute value of x minus 17 is greater than or equal to 16. All right, so again, our Chebyshev's inequality looks like this. And again, I told you that if I erase the equal sign off of here, I can put it over here. Doesn't really matter. The only reason why I erased it is because I needed to look at this compared to this. As far as events go, what are these? If I look at the inequality sign in particular, what are these? Can they happen at the same time? No. Do they encompass everything? Encompass all possibilities? Yeah, so what are they? Complements of each other, right? So if I do the complement, then the inequality is going to flip. The probability that absolute value of x minus mu is greater than or equal to k sigma is less than or equal to 1 over k squared. Just do 1 minus on both sides, it'll flip the inequality. Yeah, they'll both be equal in this case. Yeah, for the complement, either they're both equal to or they're both not equal to. It's not really that important because all we're doing is looking for a bound anyway. So if you forget the inequality when it should be there or put it in there when it shouldn't be, I don't care. Because again, all it's doing is finding a bound. All right. So for this particular problem, they've already set it up for you, right? What is k in this case? If you look at your 16, what does the k have to be? 16 over 3, right? So the probability that absolute value of x minus 17 is greater than or equal to 16 over 3 times 3 is less than or equal to 1 over 16 over 3 squared, which is 9/256. which makes sense. If your standard deviation is 3, you don't expect things to get more than 5 standard deviations away from the mean. That's 15 would be 5 standard deviations away from the mean, right? I mean, a difference of 15 would be 5 standard deviations away from the mean. You don't expect that to be a very, very likely occurrence. 9 over 256 is a pretty small fraction. You'd have to have a really odd distribution to have that much of a spread anyway. Remember, again, Chebyshev's inequality is just a bound. It's not what the probability actually is. In particular, for a normal distribution, you're nowhere near that size of probability to be 5 standard deviations away from the mean. It's nearly 0 for a normal distribution. It's exceptionally rare for it to happen. Can, but not likely. Does that make sense? So, with Chebyshev's inequality, we can look at another property of estimators that we might like to have. So, in particular, let's say that we look at the probability that the difference between the sample mean and the population mean is less than some epsilon. Where epsilon is some positive number. Oops. Well, notice I'm doing this in terms of a sample mean now. So if epsilon is some given number, I can write epsilon as epsilon times sigma over epsilon times the square root of n. Why did I choose sigma over the square root of n rather than just sigma? Oops, that's not what I wanted to do. Sorry, I need this equal to epsilon when I'm done. Sorry, try this again. I wrote kind of what I wanted, but not quite. This is what I wanted. I wanted to equal epsilon when I'm done, sorry. I want to make sure I didn't change anything. Now, why did I use sigma over square root of n here rather than just sigma? What am I interested in the standard deviation of? The sample mean, right? Right? So if sigma is the population standard deviation, the sample mean standard deviation is sigma over square root of n. That's central limit theorem again, right? So what's my k? If I want to use Chebyshev's inequality now, what's my k? Good. It's this thing, right? This is my k. If I want to use Chebyshev's inequality, that's my k. So this will be greater than or equal to 1 minus 1 over that mess squared, right? And if you simplify that, that'll be 1 minus sigma squared over epsilon squared times n. If we just simplify the algebra. Now, why do I care? So we took epsilon to just be some positive number. Think of epsilon as some very, very small positive number. Right? No matter how small I make my epsilon, so basically what I'm saying is no matter how close I say I want to look at to see when the sample mean is within a certain distance of the mean. So no matter how close I want the sample mean to be close to the population mean, I can take my n big enough and make this go to 0, can't I? Right? I can make this term get really, really small by taking n to be really, 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 really big, correct? So no matter how close I say, I want my sample means to be within a little bitty distance of the mean, you can take your n big enough to pretty much guarantee that it'll happen. Because I can make that as close to 1 as I ever want. You've done this stuff when we talk about margin of error ideas, right? How big does the sample size need to be within this region with a certain probability? That's that same idea, right? No matter how close, I want to make sure that there's some reasonable amount of probability that I'm going to be close enough to my population mean by taking my sample mean. That's a reasonable request to have, right? Right? This Chebyshev's inequality says it doesn't matter what the underlying distribution is. It's basically a central limit theorem idea. But it says it doesn't matter what the underlying distribution is. I can take this n big enough that basically cancels out this epsilon, right? Or in general, if we write it this way, for any epsilon greater than 0, we have that the probability, or sorry, write it this way, the limit as n goes to infinity of the probability that the absolute value of x bar minus mu is less than epsilon, that limit is equal to 1 from a limit perspective. So again, just thinking about it from the central limit theorem, law of large numbers perspective, all this says is that if n is big enough, your sample mean should be very, 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 very close to the population mean. That's all it says. Okay. So this particular property for sample means gives us an idea of a new definition in general for estimators. And I'll just write this definition down. I will play with it more next time. We're going to let theta hat be an unbiased estimator for theta. Then we say theta hat is consistent if this limit idea works. So the limit as n goes to infinity of the probability that the absolute value of theta hat minus theta is less than epsilon is equal to 1, and this is true for any epsilon greater than 0. Basically, what we want is that by taking a bigger sample, we're guaranteeing that our estimator will be closer and closer to the actual mean. What we don't want is something that happens that no matter what happens, no matter how large of a sample size that we get, we've always got some variance that isn't changing by much. We want the variability in the estimator to drop as we get larger and larger. Does that make sense? If we're trying to estimate something and be reasonably accurate, we want to make sure that our accuracy improves by taking a higher sample size. We don't want something to happen to where, well, once we hit some certain point, no matter what, we're still going to get this variance. Maybe your variance in terms of the sample size, I don't know how this would work as far as the random variable goes, but maybe your variance in your estimator is 1 over 1 plus n. Well, then no matter how big your n gets, your variance will never get under 1, which would stink because you would still have some sort of uncertainty in your estimator, no matter what. The whole goal of doing estimation is to try to take out as much uncertainty as possible. The only thing that you can really control with that is by taking a higher sample size. So you want to hopefully have that happen, that your higher sample size will take out variability. So that's what we'll actually do next time, is prove that to be consistent, you want the variance to go to 0. And then we'll also talk about the ideas of efficiency of estimators. So we'll see you Wednesday.
Tomorrow, you'll be in at 8 to 10 and then
Yep.
11 to 5.
Yep.
I'm going to my first. Yeah, I think